Students, today we will continue to explain Huawei's WLAN technology. Last time we talked about RTS and CTS, so in this lesson we will continue to explain interframe spacing and the random back-off mechanism in wireless communication. When sending RTS and CTS messages in our wireless communication, a certain waiting time must be followed. This waiting time is called IFS, or interframe spacing. It has two main types. ZIFs and DFs are short. Interframe spacing, times that are very short, usually 16 microseconds. They are mainly used when sending control frames, such as RTS, CTS, and ACK, to ensure they can be sent within an adequate time interval. For example, after a terminal sends an RTS frame, the AP needs to wait for the SIFS time before sending the CTS. The purpose of this is to ensure smooth communication and reduce collisions. What about DIPS? It stands for Distributed Interframe Space, used for longer time intervals, typically used after the network channel is idle. When a terminal needs to send an RTS, it must first wait for the DIFS time to ensure the channel is idle and no other communication is taking place. If the channel is clear, the terminal can initiate an RTS request. If the channel is occupied, the terminal needs to continue waiting. In the CISMCA protocol, these intervals are designed to achieve channel coordination and collision avoidance. Well, in the RTS.CTS process, when a terminal wants to send data, it first sends an RTS frame to request channel occupation. After the AP receives it, it sends a CTS frame in response. Through these control frames, other terminals will remain silent after receiving the CTS frame. This mechanism is particularly important in our multi-user scenarios, especially when the network load is high. The use of frame intervals and RTS or CTS can ensure that new resources are utilized reasonably, avoiding unnecessary interference. This mechanism of precise intervals helps maintain network stability, reduces collisions, and ensures that each user can effectively utilize network resources in multi-user concurrent situations. Now let's take a look at the key technologies in the CSMA-CA protocol, which is also a foundation of our wireless network operations. This technology specifies in the standard that the physical layer air interface conducts physical layer listening, which is extended listening. When our terminal detects, for example, that the microphone detects the channel is idle, it needs to start waiting. What is it waiting for? It's the previously mentioned DIFS, Distributed Interframe Space. Under the condition that the channel is idle, the terminal needs to wait for the maximum interval time, which is the DIFS. After the DIFS waiting is completed, the terminal can send an RTS, request to send frame. What about the AP? It applies to send data. After the RTS is sent, who is it sent to? Of course, it's sent to the AP device. After the AP device receives the RTS, it won't respond immediately. It needs to wait for the SIFS, short interframe space, first. In wireless networks, before sending any frame, there is a need to wait for an interval time, which is the SIFS. You cannot directly send an acknowledgement. This is the biggest difference between wireless networks and other communication methods. After the AP finishes waiting for these CIFs, it will respond with a CTS, clear to send. This means allowing the sending of frames. After the AP sends the CTS, all other terminals also need to wait for an SIFS time. It's important to note that in our wireless network, there might be more than one terminal. So, what are the other terminals doing? For instance, when a terminal sends an RTS to the AP, if there are other terminals nearby, they might also receive this RTS. Then they must enter into a state. Back-off mechanism. So, what is a back-off mechanism? It means the terminal will first undergo a period of dormancy, waiting for a period of time before attempting to retry, requesting a channel. So at this time, some terminals cannot send RTS. After receiving RTS, they send CTS. What is the purpose of CTS? Suppose our terminal A sends an RTS, but a nearby terminal B is relatively far away and might not receive the RTS sent by A. In that case, B might still continue to send unlimited data. This will eventually lead to a collision. However, the AP will send a CTS to inform all terminals within its range to first enter a back-off state and not send data. This forms the second back-off mechanism, which is the CTS mechanism, used to prevent other terminals from sending data. Once a terminal receives the CTS sent by the AP, it indicates that it can officially send data. It will wait for the SIF's time again, and then officially send the data. After the data is sent, it will wait for another SIF's time, and then the AP will send an acknowledgement frame, ACK, to indicate successful data reception. Once the ACK is sent, the channel will become idle, and the entire process will start over, with the channel entering again. During the DEF's waiting period, new terminals will continue to compete to send RTS. So the question is, how do terminals decide who sends RTS first? This process involves a contention mechanism, because in a wireless environment, there may be many terminals wanting to send data. Simultaneously, they must compete to determine who sends RTS first, thereby obtaining the right to use the channel. This involves our 802.11, random backoff mechanism. These two aspects are relatively difficult, and mastering this part of the content is quite challenging, so everyone should pay special attention. Moreover, there is relatively little related material available. The main topic is the backoff mechanism. We have already mentioned who sends RTS or who starts sending data after DIFS. We have a formula for calculating the practice. So, what is the practice? It is the GI backoff mechanism time. Must be an integer multiple. The actual first backoff occurs at. Choosing within 10G to the power of 2 to the power of 3, which means a maximum of 810 systems. As the number of transmissions increases, the amount of data will also increase. For example, the second time might involve choosing within 16 practices, like thus the waiting time becomes longer. But this value is random, so we'll say, suppose there are 4 terminals. The first terminal waits for 8 practices. 8 practices. The second terminal waits for 7 practices. The third waits for 2 practices. The fourth waits for 3 practices. Then the countdown begins. So who will finish the countdown first? It will definitely be terminal 3. Once terminal 3 completes its countdown, it starts sending data. At this point, the countdowns of the other terminals will enter a frozen state, meaning they will pause. Note, during the time terminal 3 is sending data, the timers of the other terminals will not count, as they all enter a waiting state. For example, terminal 3 has used 2 time slots, so terminal 1 has 6 time slots left because 8 minus 2 equals 6, and terminal 2 has 5 time slots left because 87 minus 2 equals 5. So for terminal 4, 3 minus 2 equals 1. This means terminal 4 only has 1 time slot left, so in this case, after terminal 3 finishes, terminal 4 starts its countdown and it will finish. First, then it will send data. At this time, the countdowns of the other terminals will also pause and freeze again. This is what we refer to as the random backoff mechanism, which determines the actual backoff time according to this rule. Then we will continue to discuss the hidden nodes of RTS and CTS. This was mentioned a bit earlier, for example, when a terminal starts sending RTS. After the AP receives it, since terminal 2 is not within the range of terminal 1, right? So terminal 2 does not know that terminal 1 has already sent RTS, and it will continue to send data. Yay. At this point, the AP sends a CTS to terminal 2. That is, it sends out a signal with a red tone, so terminal 2 then knows that terminal 1 has already started sending, and it needs to enter the default waiting state. So this is a very common concept. The second one is called an exposed node, which is quite special. It's somewhat similar to a function we mentioned earlier called BSS covering. This involves the transmission scenario between our AP, terminal 1, terminal 2, and the AP. Terminal 1 and AP1 are exchanging data with each other. Meanwhile, terminal 2 and AP2 are also exchanging data with each other. In other words, the two transmissions themselves actually have no impact on each other. I transmit mine, you transmit yours without any impact. However, because the distance is too far, when terminal 1 sends an RTS, terminal 2 will also receive it. When terminal 2 sends an RTS, terminal 1 will also receive it, and at this point, a significant impact will occur. Because terminal 1 might mistakenly think that terminal 2 is also transmitting, causing it to enter a waiting state, or terminal 2 might think terminal 1 is transmitting, and it will also enter a waiting state. At the same time, when the AP sends a CTS, terminal 2 might not be able to properly receive the CTS, leading to abnormal data transmission. This is what we commonly refer to as the exposed node problem. In this situation, the AP or terminal will only respond based on the CTS it receives, ignoring the previously received RTS, meaning that RTS is only used to reserve the channel, and the final transmission decision still depends on the CTS response mechanism. This is the scenario of the exposed node. This issue corresponds exactly to some of the typical working mechanisms of wireless network communication we mentioned earlier. It is one of the classic problems in 802.11 networks. In the following sections, we will also explain the roles of RTS and CTS messages and what specific types of messages they belong to. Now, let's first take a look at channel bonding. Channel bonding refers to combining multiple non-overlapping channels to increase the transmission rate. It is important to note that in channel bonding, we designate one channel as the primary bandwidth and another as the auxiliary bandwidth. For example, if we bind channel 1, or specifically, channel 149 with channel 153, we can represent it accordingly. In this setup, the primary channel is responsible for the main packets, while the auxiliary channel handles the transmission of other packets. Under this bonding method, the primary channel bears a larger data load, such as when sending main data packets, while the auxiliary channel handles the transmission of auxiliary data packets. These packets are responsible for the management and discovery of the wireless network. Therefore, the distinction between the primary and auxiliary channels is very important. Especially in terms of identification methods, differentiation is also achieved through addition and subtraction. Additionally, in our bandwidth bonding scenario, it is usually represented by the central bandwidth. This bonding method allows for more efficient utilization of channel resources, which also takes into account interference between channels and the allocation of squares. For instance, in this source bandwidth, we typically use a 40 MHz bandwidth. Alright, that's all for today's sharing. If anyone is interested in Huawei's certification or Huawei's question bank, feel free to leave a comment below my video. If you have any questions about the WLAN technology I explained, you can also leave a comment below my video, and I will respond to everyone.